Welcome to this video all about organic mechanisms. We're going to go through the 5 organic mechanisms that are in the IB/HL chemistry. The first one is also in the SL if you're an SL student. So let's get started on these mechanisms and the common mistakes that people make when they're drawing them. Free radical substitution is the only mechanism that is in the SL content. So let's go through that one first. Let's define what free radical and substitution means before we get started. So a radical just means something that has a single unpaired electron. And what I mean by that is normally when we're drawing dot and cross diagrams or Lewis diagrams, you're drawing your electrons in pairs. If something doesn't have a pair and it's just got one like single electron within those orbitals, then that means that we call it a radical. Now, those radicals are generally really super reactive because, as you know, electrons tend to exist in pairs and that has increased stability associated with it. Substitution, if you're asked to define that, just means that essentially you're swapping functional groups. So we're swapping one functional group for another during the reaction. So this overall is going to be called free radical substitution. In general, it happens when you've got an alkane reacting with a halogen. So by halogen, halogens are diatomic molecules. So I mean like Cl2, Br2, I2. In general, could be any of those halogens, and them becoming a halogenoalkane and a hydrogen halide. So this could be HCl or HBr, etc., etc. So overall, that's the process that we're talking about. As an example, let's get into those as soon as possible. We've got this here, the ethane. So ethane looks like this. So we've got C2H6, and that's going to be reacting with bromine. Remember, it's diatomic, so Br2. And that overall is going to turn into bromoethane, So we are swapping one of the H's, which is not really a functional group. A hydrogen isn't really a functional group, but we still use that terminology here. So we swap a hydrogen for a bromine, and then that leaves a hydrogen and a bromine left over. So that's where your hydrogen bromide comes from. So the question is, like, how does the mechanism work? How does it really happen that the ethane plus the bromine does this like reaction and you end up with these products? What's the middle step, the pathway to get there? In this case, it's split into 3 stages: initiation, propagation, and termination. And if you're asked for this mechanism, it will probably be worth 4, maybe even 5 marks in total, so it's definitely worth getting right. So in the initiation phase for this reaction, it actually only includes the bromine molecule, the Br2. Now, bromine exists as a diatomic molecule, and you've got that shared pair of electrons in the middle like this. Now, what happens in this first step is one of these electrons goes to one bromine and one goes to the other bromine. And so what we end up with is 2 bromine radicals, and this is the notation for radical, this like dot in the right hand corner. I strongly recommend you do what I did and like do a circle and color it in, because if you just do like a dot with your pen, then the examiner might not see that and you might lose marks even though you knew what you were doing. So here we've got the bromine going to the 2Br dot or 2Br radicals, and this happens in the presence, let me change color to make it obvious, happens in the presence of a photon or ultraviolet or visible light, depending on which halogen you have, depends on what frequency of light you require. So we use this shorthand here, the H, which is Planck's constant, and the nu, which is your frequency, which is kind of a shorthand for like energy, radiation, photons, like to break it down. So the bromine takes in some photons and then it splits it apart, and that energy it uses to make 2 bromine radicals. Let's go back to actually let's leave it in blue. So the propagation steps is really what happens to these radicals to react with the ethane. Remember, we're trying to make this bromoethane overall. So let's have a look at how we might get there. So this Br dot, the bromine radical, reacts with the ethane, which I'm going to shorthand to C2H6 in this case. And what happens here is because the bromine radical is so reactive, it's able to essentially pull one of the hydrogens from the ethane molecule. So I'm going to make HBr. And every single time in this first step of propagation, you're always going to have like your halogen radical going to H halogen. So you just make everything else kind of fit around that. So we're going to add whatever's left over. So I've got my C2H5 now because one of the hydrogens was lost to the radical. And that means that this overall has become a radical. So in the initiation step, we went from like something that was not a radical to a radical, whereas in propagation, I'm now going from something that is a radical to still a radical. It's like just passing the radical status along. So there'll be a radical on both sides of these equations. Propagation normally requires you to show at least 2 steps, and what I'm showing you is the steps that would normally appear on a mark scheme, but there's a variety of propagation steps that are valid, like any radical reacting with anything that's not a radical essentially. So we're going to take this ethane radical, this C2H5 dot, and we're going to react it with the Br2. So we're going to react it with the halogen molecule, whatever that was in your example. That then goes to your C2H5Br, because remember that radical just wants to pull anything towards it. It wants to get rid and pass on that radical status as quickly as possible. And then that leaves my bromine being regenerated, my bromine radical being regenerated in this step. So you can see that here I've made that bromoethane overall as a product of this reaction, which is all good. Let's look at the last step, which is a termination step. So in this step, you're trying to get rid of the radicals. So the only way to do that is by combining any radical with any other radical. So let's have a look. So here we can take our bromine radical, and theoretically that could run into another bromine radical and make Br2. So essentially the reverse of your initiation step. And this is a perfectly legitimate termination step to get you 1 mark. So normally you've got 1 step for initiation, 2 for propagation, and 1 for termination to get those 4 marks overall. Termination could be other things though. We could take our C2H5 dot, and theoretically that could react with a bromine radical, and then that makes C2H5Br, so again making my bromoethane product. So in this case, there's actually loads of different ways to demonstrate how you would make bromoethane, your final product in this reaction. But there's also no way to stop this reaction. So with free radical substitution, it will keep going on and on and on because your bromine radicals keep getting regenerated. So it will keep substituting those hydrogens out, potentially until it's taken all of them, depending on how much bromine you start with in your reaction. So just to be aware, this is a chain reaction. There's not just one product. It could become 1,2 dibromoethane or 1,2 tribromoethane. Like, it could keep regenerating, and you have no way of really knowing where it's going to stop unless you control the conditions of the reaction. Let's move into the HL content and talk about nucleophilic substitution. Now, these are the mechanisms that you probably need to know the most about in HL, so it's worth spending some time here. The word nucleophilic, literally if you break it down, just means nucleus loving. So if we describe something as a nucleophile, it means it is attracted to a region of positive charge because it itself is probably negatively charged, or at least has a lone pair of electrons. So attracted to a region of positive charge. And we can say that 9 times out of 10, it also will have a lone pair. So if something has a lone pair, it could probably be capable of acting as a nucleophile. Substitution we defined in the last section, so we're all good. And the first mechanism that we're going to look into is the SN1 mechanism. Now the S just stands for substitution, the N stands for nucleophilic, the 1 is what makes it a bit special, and that's that it is unimolecular. Now this tells us about the overall order of reaction. So this means that overall the order of reaction for this nucleophilic substitution is 1. So it is first order with respect to one reagent. So I'm expecting that my rate determining step only includes one species. So let's have a look at how that pans out. This example, the SN1, also is almost exclusively what happens to tertiary halogenoalkanes. So if you've got a tertiary halogenoalkane like we do here, then we would expect it to follow the SN1 mechanism. So let's have a look at what that looks like. So for both nucleophilic substitution mechanisms, you've got halogenoalkanes reacting with a hydroxide ion to make an alcohol and a halide ion. So obviously these hydroxides and halides are probably attached to a sodium or a potassium ion, but that doesn't influence the reaction, they're just spectator ions. So overall, as long as it's got a hydroxide, then you're looking at this mechanism happening here. So let's draw out our example so that we know what we're working with. So here I've got propane, so I know it's based on 3 carbons. And on carbon number 2, I've got a bromine atom. And on carbon number 2, I've also got a methyl group, so a CH3, which I'm going to draw like this. On all the rest, I'm going to add hydrogens to saturate those carbons out. So this is the species that we're going to deal with. It is a tertiary halogenoalkane because, as you can see, this carbon here hasn't got any hydrogens on it, and it has 3 carbons attached to it, making it tertiary. And then this reacts with, it says sodium hydroxide here, so NaOH, but remember that sodium is going to be a spectator ion. And then that is going to become 2-methyl-propan-2-ol. So we're going to draw exactly the same compound, but instead of this bromine in the middle position, we're going to put an OH group. Now be really careful when you're drawing OH groups, because if you draw it like this and put the hydrogen here, it kind of looks like the bond is attached to the hydrogen versus attached to the oxygen, and you could definitely lose marks for that. So if you're drawing a bond to an OH group, be super cautious that your O is the part that's actually attached to the bond itself. No matter how you have to draw it, that's the most important part. Everything else in this molecule is staying exactly the same. So I'm going to add all these hydrogens in, the methyl group's still in the same position, all A-OK. And then we're also going to make, oh, this is a mistake. This should be sodium bromide, so it should be NaBr here. Apologies. Let's look at the mechanism for this reaction and how we turned that tertiary halogenoalkane into a tertiary alcohol. So we're going to start with the tertiary halogenoalkane because actually this is the only species that is involved in the first step, and that's why it is unimolecular, because this first step, which is the rate determining step, is only dependent on this halogenoalkane, the tertiary one. So what happens first is that the bromine in this molecule breaks off, and the way that we show that is I'm going to draw a curly arrow from the bond to the bromine. So that means that the electrons in that bond are going to the bromine. So when we're drawing curly arrows, the rules is that your curly arrow should always, always, always start at a bond or at a pair of electrons, like a lone pair of electrons. They should always start at a bond or a lone pair. And they should be going towards the thing that's going to take the electrons or to where the bond is going to be formed. So here the bromine is stealing those electrons. So let's draw what the after of this looks like. So most of this species looks the same. These hydrogens are still here. This CH3 is still here. Notice how that CH3 has the carbon attached to the bond and not the hydrogens. But there's a gap in the middle here, and that is now a positive charge. And we call this a carbocation intermediate. Now that cation means it's positively charged, carbo just means it's a carbon that's positively charged, and this species can hang around for a little bit, like it exists for a small amount of time, when that bromine has broken off. So when the bromine's broken, it becomes Br-, existing like that, and then the OH-, the hydroxide ion from my sodium hydroxide, which has a lone pair, let's draw another arrow in blue to be consistent, can come in here like this and bond to that middle carbon, hopefully to make the bond overall. So you can see my arrow started from a lone pair and it's going towards like where I'm going to draw the line where the bond is. So let's draw the after. So here the after is going to be the OH in the middle like this. The methyl group is still there and everything is completely saturated. You've also got the Br- still existing as a byproduct, so the bromide ion is still there overall. So this is overall your SN1 mechanism. This could be worth 4 marks in an exam, so you get 1 mark for that first arrow of the bromine leaving, 1 mark for the bromine, 1 mark for this hydroxide arrow, 1 mark for the carbocation intermediate, and then 1 mark for the products. That's including the bromide ion. So don't forget that bromide ion at the end is the most easy thing to miss for this question. Let's have a look at SN2 and how that is different. There is another way that the reaction could go between a halogenoalkane and a hydroxide ion. So we call this mechanism SN2. So it's still substitution, still nucleophilic, but in this case the 2 means that it is bimolecular. And that just means that the overall order of reaction is now 2 rather than 1 like it was in the previous example. This mechanism is like predominantly followed by primary halogenoalkanes. And so if you've got a primary halogenoalkane, you can predict that it probably goes this way. You might be thinking, what the hell happens if I've got a secondary halogenoalkane? And the truth is that it's not so easy to predict which mechanism it's going to follow. So the easiest way to do it is to look at the overall order of reaction. So if your overall order of reaction is 1, if it only depends on the halogenoalkane, then you know that it's following SN1. If it's like dependent on both the halogenoalkane and the hydroxide ion, if it's first order with respect to both, then you know that it's following the SN2 mechanism. So quite often they will combine one of these questions with a kinetics question to help you to kind of gel all of that knowledge together. So please go and check out some of those because they're quite interesting to look at overall. So let's crack on with an example here. I've chosen 2-bromobutane. So 2-bromobutane is actually a secondary halogenoalkane. And you might be thinking, she just said that this one was done by primary halogenoalkanes. Why might she pick a secondary halogenoalkane? And the truth is because I also wanted to demonstrate to you what happens to the stereochemistry in this reaction, because SN2 shows an inversion of stereochemistry, which only happens really, like observably, with things that have chirality. This is the simplest thing that has a chiral center. So this 2-bromobutane, this carbon here is actually chiral. So it contains the bromine, the methyl, the ethyl, and the hydrogen, so 4 different groups. So it has enantiomers, it shows stereoisomerism, and so we can use it to demonstrate in the mechanism later what happens to the overall stereochemistry. So yes, it's secondary, but it's all okay. This reacts with sodium hydroxide to make butan-2-ol. So again, that OH is just replacing the bromine. So it's going in position number 2. And I'm going to fill the rest with hydrogens because nothing happened to these guys overall. Okay? And then we're getting sodium bromide as our byproduct, just like last time. All right, now let's look at the mechanism. Now, the way I'm going to draw this is I'm going to show the stereochemistry of this 2-bromobutane by drawing it in 3 dimensions. So when I draw it, I'm going to show the bromine on this side just to make it a little bit easier for myself. And then I'm going to put the hydrogen in the same plane. Then I'm going to have a wedge, which means that section is coming out at me. And we're going to put the CH3 here, and then we'll show 1 dash going back, the C2H5. So this is showing the tetrahedral shape around that carbon in this middle there. Okay, all good. So this, in the first step, is going to react with the hydroxide ion. Notice how I always put a circle around my charges just to make them kind of extra clear for like an examiner or somebody who's looking at it, because if you just like gently do a dash, again, they get lost quite easily. So try and be really intentional with showing your charges. Let's look at what happens in this first step. So in the first step, you've got the hydroxide ion being attracted to that carbon and the bromine atom being lost simultaneously. The reason this happens is that the bromine is delta negative. It's got a slight negative charge because it's more electronegative than the carbon, and the carbon is delta positive. So that means that this hydroxide group is attracted to this region of positive charge. So that means the hydroxide is the nucleophile. And we can show that by the lone pair forming a bond with the carbon, and then the electrons in this bond are going to the bromine as it gets lost. In the second step of this, we actually show a transition state, so kind of what it looks like in the middle. So watch the way I draw this. So we're going to start with the bromine, which is being lost, so we're going to draw it as a dotted line, and then 180 degrees to that, I'm going to draw the hydroxide group that's coming in. It's a hydroxyl once it's in and a hydroxide outside, so let's not be too pedantic. And we're going to draw a transition state, so we're going to put it in nice square brackets here, and overall it's going to have a negative charge. So if I have a look at this species here, you can see that there's a hydrogen that's still going to have a normal arrow, like a normal line, like it's still in the plane. We've got the CH3 group, and I've also got a C2H5. So the way I'm showing this is that essentially it's like an umbrella inverting. So as the hydroxide comes in to bond to that central carbon, you can see it's pushing all of those other atoms over to form a tetrahedral on the other side. Let me show you the after so that you can kind of see a bit more what I mean. So afterwards, remember the bromide has been lost, it's already gone. So the hydroxyl group is now attached here, and remembering that O has to come first. The hydrogen is still staying with the same kind of line to make it a bit easier. The CH3 is here, and then with my dashed line, I'm going to have my C2H5. Notice how the lines, I'm being really specific about which atom it's attached to. So I reversed how I wrote the CH3 to show that the bond was to the carbon and not to the hydrogen. So hopefully you can see here that the stereochemistry has been inverted. So the tetrahedral went from one way to the other way as the hydroxide ion came in. If you're looking for what's giving you marks here, you're getting a mark for this first arrow, this second arrow being correct, for the transition state being correct, and for the products being correct. So 4 marks overall. You might pick up another mark for the inversion of stereochemistry and talking about that in a bit more detail. But this is how you draw it in 3D, which you should definitely be comfortable with. Electrophilic addition is the mechanism that we use for all of the alkene reactions that you've got in IB Chem. So electrophilic just means something that's attracted to a region of negativity, electro meaning like electrons are negative. So we can just say attracted to a negative region. So that means that an electrophile overall always has a positive charge or a delta positive at least, so that you can show its reaction overall. Addition just means the same as it does in math and in other areas, where two or more molecules combine to make one. So we're making one molecule overall, so 2 things making one is an addition reaction. There are no byproducts in these reactions. So the most common one that we're going to use as our example here is we've got an alkene plus a hydrogen halide, makes a halogenoalkane, but it's important to note that if you react an alkene with a halogen, so like Br2Cl2 or water to make an alcohol, all of those alkene reactions where they're popping open to add things on, all undergo this mechanism. It's just that this is the one that's most commonly asked about when you're asked to draw the mechanism. So the hydrogen halide we're going to use today is HBr, but we could equally use HCl. I just steer clear of the Cls because the Cs look like carbons and it's like less clear overall what I'm doing. And they combine together to make the halogenoalkane. So the one that I've chosen to use today is propene, so that means there's 3 carbons. The ene means that there's a double bond, so we can show a double bond here, and then we can add the rest of the hydrogens to make sure that every carbon has 4 bonds. Resist the urge to put a hydrogen here because it shouldn't go there. That carbon has already got 4 bonds on it, but sometimes when you're like adding all of the hydrogens on, it's really easy to add that extra one by mistake. We're going to react it with HBr, hydrogen bromide, and that double bond is going to pop open, and then the hydrogen is going to add on the left-hand carbon, and the bromine is going to add onto the middle carbon. That final carbon is still staying the same as a methyl group. You might be wondering, well, how does she decide that it was going to be 2 bromopropane and not 1 bromopropane? Like, if it pops open, surely it can go on to carbon number 1 or carbon number 2. And that is true, but this is the major product. And we'll talk about why that is in a second. So let's look at the mechanism and a bit more detail of how this works. So for this reaction, let me just redraw out my propane. The propane has that region of negativity. The double bond is a region of negativity because you've got all of those electrons in those pi orbitals that are hanging around there, making that a really negative space overall. They're going to react with the with the HBr. Now the reason that that's attracted to the region of negativity is because bromine is way more electronegative than hydrogen is. So that means that these electrons in this shared bond are way more towards the bromine side than the hydrogen. So this end is delta negative, this side is delta positive, which makes a really big difference here. So what's going to happen, let's draw the curly arrow, is that the electrons in this bond here, the double bond here, are going to be attracted towards this delta positive hydrogen, and they're going to form a bond with the hydrogen, and then the electrons from the bond are going to go to the bromine just like they did in the nucleophilic substitution, and we're going to form the bromide ion over, like, temporarily in the middle step. Okay, now the problem is that this could theoretically form 2 different products. So let me show you what I mean. So if we'll go up top here first. If when this pops open and attaches onto the hydrogen attaches onto this carbon number 1, then that means that the carbon in the middle is now going to have a positive charge on it. It's another one of those carbocation intermediates, same as nucleophilic substitution. If, however, when it pops open and that double bond breaks up, the hydrogen goes onto this middle carbon here, so we're going to leave 2 hydrogens on this side. There's another one there, and then some here. So now you can see the positive charge is on carbon number 1. So this is what dictates actually which is the major and the minor route of this mechanism. So the most stable carbocations are tertiary carbocations, followed by secondary, followed by primary. So this example at the top here, this carbocation number 1, is way more of a stable carbocation because you've got a positive inductive effect from the 2 carbons around it, whereas in carbocation number 2, I've only got the positive inductive effect from 1 carbon atom next to it. So what that means is carbocation number 1 is way more stable, and so that means that it will preferentially form carbocation number 1 over carbocation number 2. So in the next step, the bromine, remember, was formed, and it forms this bromide ion because it stole both of the electrons from that bond. And if we add the curly arrow to it, the bromide is going to could add on to either of these. Actually, let me do that separately to make it clearer. So here, and then let's put another one on, another Br minus, and then remember we're drawing the arrow from the lone pair into the, like where the bond would form. So you can see that the final overall options are that the bromine could have added to the middle carbon here, or it can add to that first carbon, like in this route. So we call this Markovnikov's rule, because he's the dude that came up with it. And the rule kind of goes that the hydrogen in the first step will add on to the carbon that had the most hydrogens. So in my first molecule here, carbon number 1 has 2 hydrogens, and carbon number 2 only has 1 hydrogen. So that means that the hydrogen is going to add on to carbon number 1. So overall, we've got our major product, which is the 2-bromopropane, and the minor product, which is the 1-bromopropane. So both of these can form, it's just that one is formed in higher quantities than the other one because of the increased stability of the carbocation. Okay, last mechanism. This one is electrophilic substitution, and this is the only example that exists for this. So if you know this one, then there's really not much more that they can throw at you, to be honest. So this is the reaction between benzene and the nitronium ion, which is NO2 with a positive charge. It makes nitrobenzene and a hydrogen ion as the products. So rather than showing the example reaction, because this really is an example, this box has now become how to make the nitronium ion, which is something that gets asked here, because I can't just buy a bottle of nitronium ion, it doesn't exist. So the way that we make that is that we react concentrated H2SO4, sulfuric acid, and concentrated nitric acid, HNO3. Now you might be thinking oh, but acids don't react with each other, which is normally true, but if they're both super concentrated, then actually what you find is that depending on the strength of the acid, they actually can have some proton transfer between them. So because the sulfuric acid is actually a stronger acid than the nitric acid, even though both are classified as strong, sulfuric is stronger because it's all a spectrum, that means that the hydrogen from the sulfuric acid can be transferred to the nitric. So overall, that will give me HSO4 minus, because it lost a hydrogen ion, and H2NO3 positive, because it gained that hydrogen ion. Now the way the nitronium ion is formed is if this H2NO3 positive, if this species then breaks up, it can form the NO2 plus and water. So this is the only way that we make the nitronium ion, and this is something that you should be able to illustrate in your examples. So now it's mechanism time. So let's draw out the benzene first, using a circle to illustrate those delocalized electrons across the whole structure. And that's going to react with the NO2 positive. So this is electrophilic substitution. So electrophiles, remember, are attracted to regions of a negative charge. So the delocalized electrons, the ring, is my area of negative charge, and the NO2 plus is the electrophile. So the arrow that I'm going to draw is going to come from the ring, from those delocalized electrons, to the nitrogen in my nitronium ion. Now, what that's going to give me is the nitronium ion will have added onto one of the carbons, and because I drew my arrow kind of through that carbon in position 2, I'm going to add it on there. And then I'm going to show that it has broken this ring of electrons. I took some electrons from that ring, so now it's not a complete delocalized ring anymore. So overall, that's going to have a positive charge. Notice how the ring that I've drawn kind of almost goes towards the place I added the NO2. So wherever you're adding the NO2 on, you need to show the gap in the ring kind of corresponding to that. Don't show it too big, don't show it too small. It should kind of be about the length of like a third of it, so don't go too crazy. And let's look at what happens next. So this carbon now has two things attached to it. It has the NO2 and it also has a hydrogen attached to it. So the only way that we can form our nitrobenzene, which is the benzene ring with an NO2 group on it, is to get rid of that hydrogen. So it actually gets lost as a hydrogen ion. So it donates both of its electrons into the ring to then reform it and to make that stabilized structure. Let me show you. So we're going to put an arrow from the hydrogen into the ring, and that is the final arrow that we need to draw here. So if you're getting marks for this, you're getting 1 mark for this first arrow here, 1 mark for this structure, 1 mark for the second arrow, and then 1 mark for the final products, not forgetting that H+ ion as a product. That is all for this video and the organic mechanisms in IB chemistry. I recommend that you draw out all 5 mechanisms in detail and then you show them to your teacher to check that you've drawn all of the arrows in the right places and that you haven't randomly lost any negative charges or products and things like that. It's really easy to make minor mistakes in your notes that then you think are correct and then you end up getting it wrong in exams and things like that. So make sure that your notes are 100% correct for this, or just email them to me and I'll check them for you. All right, see you next time.